Okay, welcome back to Unit 3, Work Energy and Power. Here we're going to focus on kinetic energy and the work energy principle, also known as the work energy theorem. Kinetic energy is probably something you've worked with since middle school. Again, it's going to be that same concept of energy and motion, but we're going to connect it back to the first two videos when we talk about work done. So the first thing is, remember, energy is one of the most important concepts in science, okay? Not just physics, but in science. The crucial aspect of energy is that the sum of all types, or what we call the total energy, sometimes also called mechanical energy, is the same after any process as it was before. So what we say is energy is a conserved quantity. Okay, this is very important, and we're going to talk about really three types of conserved quantities here in mechanics. Energy is going to be the first of the three, then you're going to talk about momentum, and then angular momentum. All right, so energy and motion, just like we talked about, is called kinetic energy. One thing that we do now, again, in physics, is we bring in an equation. So kinetic energy is simply 1/2 mv squared. So 1/2 mass times speed squared. Okay, and then now we connect it back to this work energy, or to energy, or excuse me, to work. So the net work done on an object is equal to the change in the object's kinetic energy. And I want to point out that is very important. It's not equal to the kinetic energy. It's equal to the change in the kinetic energy. And make the note of this. Okay, it's only for the net work done on an object. Okay, so all the individual forces that are acting in the object will do work on an object, but when we talk about the work energy principle, it's only for the work, or excuse me, the net work done on an object. So what we say is we can take that definition and turn it into a mathematical formula to where we say the work done is equal to the change in kinetic energy. But we can also substitute in these equations, right? So we can do F dot D. We can do, but we know F dot D is FD cosine theta, okay? And then you can also bring in that the integral from x0 to x of F dot dx, right? All that equals work, but again, then kinetic energy, or change in, is 1/2 mass times V final squared minus V initial squared, right? Or you can write it like 1/2 mv squared minus V initial squared, or sorry, this should be 1/2 mv initial squared. Okay, so one thing to note here, again, this is what drives math teachers crazy, is that these two, right, are not the same. They don't equal each other. Okay, so we don't want to do that. So we're doing the difference of the squares of the speeds, right? And so you can find all kinds of things from this. So if I write this out completely, because I've got that delta K running around in the middle there. So I get FD cosine theta equals 1/2 m V squared minus V initial squared, right? And so all the way from up there, we can write it as such. You may have to find the acceleration. So remember, F is m times a. Okay, so there's all kinds of things that you can do mathematically with this equation. So let's look at an example. Actually, we're going to look at two examples. So first thing, we got a baseball's thrown. It requires 25 meters per second of speed. What is the kinetic energy? What was the net work done on the ball to make it reach the speed if it was started from rest? So simply enough, for part A, this is a very easy calculation. It's just going to be 1/2 mv squared. So I'm going to go 1/2. Now remember, our mass needs to be in kilograms. So it's going to be 0.4145 kilograms. And we're going to go to 25 meters per second squared. Okay, so we have done 45.3, or given it 45.3 joules of energy. Okay, now how much work was done if it was starting from rest. So now this is where we applied our work energy principle or theorem. So we know we have 45.3 joules in the end. Starting from rest, it has 0 joules. So the work done by the net force on this ball, right, is also 45.3 joules. So if it started at a different speed, that number would be different. But because the initial velocity, or it says it tells us it started from rest, it's going to be the same value. Okay. So now let's look at one more, the car stopping. So you got a car traveling at 60 kilometers per hour, coming to a stop at 20 meters. If the car is going twice as fast at 120 kilometers per hour, what is the stopping distance? Assume the maximum braking force is approximately independent of speed. Okay. So we can do this conceptually. Okay. So I've got work equals delta K, right? So we're going to apply our work energy theorem. But work, again, is going to be FD. Now, the cosine angle, okay, we're just going to leave it as such. And then so I got K minus K0. So my final velocity would be 0. And so this would be F equals M mass times acceleration. We know that K is 1/2 mv squared. So the m's would cancel out. And so it tells me that acceleration times distance is 1/2 v squared. So really, if you want to talk about these, would be both of these would be, all this would be negative, so that these will all become positive. So what we're really doing here is we're looking at a relationship between distance and speed. And so velocity squared is equal to 2AD. So look, so my accelerator, it tells you the braking force is approximately independent of speed. So that means my acceleration is not affected by the speed. So essentially acceleration is constant. So we can apply our factors of change, right? And so I double the speed, right? 2 stays the same, acceleration stays the same. So what happens to my stopping distance? Well, my distance is going to go up by a factor of 4. So if my initial at 60 kilometers per hour, I stop at 20, what happens to when I stop at 120 kilometers per hour? Well, that's going to be 80 meters, right? Because I'm going to stop out 80, excuse me, not 80, but I'm going to stop out 4 times as much as if I was trying to stop at 60 kilometers per hour. You can, once you get this v squared equals 2AD, I can do the algebra, right, to get to my point. That's an equation that looks very familiar, right? You can see though, like the V's, the V and the V0 would be different, okay? But the problem with that is then you would need to find what is the acceleration. And there's really not enough information here to find the acceleration, but we can use our relationships. And this tells us that V squared is proportional to the distance, okay? So that's how we can use the work energy theorem to solve a problem like this. Okay, in the next video, we're going to start making our shift from kinetic to potential energy, which is where we're going to end up with doing a fair amount of calculus.